In February 1942, amid the heat and chaos of the Pacific War, a Boeing B-17 Flying Fortress sat abandoned on the airfield at Yogyakarta, Java. The aircraft's American crew had fled just hours earlier, retreating before the rapid Japanese advance. Though the bomber had been damaged during a crash landing, its structure remained largely intact. It would not stay undiscovered for long. Japanese forces, sweeping through the Dutch East Indies, encountered not just one, but several B-17s across captured airfields. These aircraft were far more than battlefield relics. They were windows into a different world of manufacturing, and the Japanese engineers who examined them would come away changed forever. Within weeks, teams from Japan's Elite Air Technical Research Institute, the Koku Jijutsu Kenkyujo, arrived to begin evaluating the captured bombers. Based at Tachikawa Airfield near Tokyo, this institution represented the height of Japanese aviation science. Now, its engineers were presented with a puzzle unlike any they had solved before. The Americans had left behind not only their bombers, but also instruction manuals, spare parts, and maintenance facilities. Using salvaged components and Allied mechanics pressed into service, the Japanese worked tirelessly to restore two of the B-17s to flying condition. It was not easy. The electrical system's hydraulics and engines were unlike anything seen in Japanese aircraft. But slowly, through months of careful study, they succeeded. And in 1943, two restored flying fortresses flew from Java to Japan, accompanied by fighter escorts and shadowed by a converted transport aircraft. Once in Japan, the real analysis began. Engineers carefully disassembled every component of the bombers. They measured rivet spacing, checked material thicknesses, and tested system integrations. What they found was stunning. The construction of the B-17s revealed a level of standardization and mass production previously unimaginable to Japanese technicians. Parts from one aircraft could be swapped into another with no adjustments. Panels were identical across multiple bombers. Even the smallest details, the spacing of rivets, the alignment of electrical wiring, the fit of engine parts, followed exact specifications. This wasn't the result of master craftsmen carefully shaping individual pieces. It was a product of a deeply organized, highly repeatable system. The differences were stark. Japanese aircraft were often hand-assembled by skilled workers. No two planes were exactly the same. If a wing was damaged in combat, a replacement part often had to be modified to fit that specific airframe. In contrast, American bombers like the B-17 had been built in massive factories, with automated riveting machines, stamped parts, and tooling designed to eliminate human variability. The engines in particular left a lasting impression. Every component was machined to a precision measured in thousandths of an inch. Parts could be interchanged freely between engines, something unheard of in Japanese designs, where components were often hand-fitted and required expert adjustment. Even more telling was the way systems like hydraulics and electrical wiring had been simplified for ease of maintenance. Japanese aircraft typically required skilled electricians or armament specialists for repairs. In the B-17, components were modular, color-coded, and standardized, allowing relatively unskilled mechanics to make rapid replacements using basic tools. The gun systems followed a similar philosophy. American machine guns were crude by Japanese standards, built with loose tolerances, but they were robust, easy to maintain, and reliable under combat conditions. It was a different engineering mindset entirely. The Americans didn't design for perfection. They designed for scale, speed, and reliability. By 1943, the Japanese were flying all three captured B-17s in regular test flights. Fighter pilots trained against them. The bombers appeared in propaganda films, sometimes repainted with American insignia and escorted by captured Allied fighters to simulate realistic air combat. But even these efforts couldn't mask the growing awareness among Japanese engineers and military planners. The United States had built an air force that could not be stopped simply by shooting down planes. For every bomber lost, the Americans could build 10 more. Japanese fighter production, dependent on a shrinking pool of skilled craftsmen, couldn't keep up. This realization forced a deeper reckoning. The B-17 wasn't just a powerful aircraft. It was evidence of a production system that Japan couldn't match. Japanese engineers began documenting every aspect of the bomber, publishing technical analyses, and producing internal manuals that studied the aircraft down to the rivets. One engineer noted the simplicity of the B-17 cockpit, despite the aircraft's size, as a sign of sophisticated systems integration. Another acknowledged that while the B-17's design dated back to 1935, it had evolved into a first-line combat aircraft through intelligent upgrades, a process made possible by standardized production and system-level design. What these reports didn't say outright, but what every reader would have understood, was this: Japan's aircraft industry was not equipped to win an industrial war. The factories weren't large enough. The processes weren't efficient enough. The workforce, though highly skilled, could not scale fast enough to meet wartime demand. In contrast, American factories were producing 16 B-17s per day at Boeing Plant 2 alone. By the end of the war, more than 12,700 B-17s had been built by Boeing Douglas and Lockheed Vega. The result of a nationwide, coordinated industrial effort that no Axis power could match. The captured bombers, once testbeds for engineering curiosity, became silent witnesses to a growing sense of inevitability. Japan could not compete in a war of industrial attrition. The manufacturing methods embedded in the B-17 revealed this truth more clearly than any battlefield encounter. And when the war ended, those same engineers who had studied the bombers so carefully carried their lessons into Japan's post-war recovery. In the decade that followed, Japanese industry transformed. The skilled craftsman remained important, but his role changed. Instead of hand-building individual components, he now designed tools, machines, and processes to produce those components systematically. Factories once relying on manual labor adopted precision tooling and automation. American production methods were not merely copied. They were refined and improved. The result was a rebirth of Japanese manufacturing, one that by the 1970s had surpassed many American companies in efficiency, consistency, and innovation. Ironically, by the 1980s, it was American engineers who traveled to Japan to study the very manufacturing systems that had evolved from those wartime lessons. Toyota's just-in-time production, Honda's precision machining, Sony's electronics, all bore the fingerprints of a nation that had once been humbled by a handful of bombers left on an airfield. The B-17 Flying Fortress, which dropped over 640,000 tons of bombs during World War II, earned its fame through firepower and endurance. But its greatest legacy may lie not in the missions it flew, but in the lessons it taught. When Japanese engineers dismantled those bombers, they found more than aluminum and wires. They found a blueprint for industrial supremacy, a philosophy of manufacturing that valued systems over individuals, standardization over customization, and mass production over masterwork. Those bombers are gone now, lost to time and war. But the knowledge they gave lives on. They taught a generation of engineers how to build a better future, not by copying the shape of an aircraft, but by understanding the system that made it possible. That understanding became the foundation of Japan's industrial rebirth and reshaped manufacturing around the world. The Flying Fortress, in its unintended role as teacher,